Today we're going to be relating scale and proportions and using them, using proportions to solve scale problems and also setting up and solving other word problems with proportions. So here are the key concepts. You don't have to write down all the definitions. A scale drawing, we're talking about like a map would be considered a scale drawing. A blueprint of a house would be a scale drawing. It's a drawing of an object that is reduced to a proportion of the original. A scale model would be a 3D model of that thing. Sometimes before they build skyscrapers, they make a 3D model that shows all the parts of the building in proportion to the actual building. And so the scale is the ratio of the dimensions of the larger object to the reduced object. Maps, globes, Google Maps, blueprints, and model cars are all examples of scale drawings or models, and it makes it easier to understand the larger objects. So I know that in geography you guys have had experience of using map scale. Today we're going to use a proportion to calculate some of those types of problems. When you're looking at actual measurements, if you're on a map, the distance between El Capitan and Panorama Cliff is 2 inches. What is the actual distance? So if we know in inches and we know the scale, which in this case we do, so this won't be an example, but I'm going to show you down here is the scale. We know we could set up a proportion such that we have our inches to miles. So our scale would be 1 to 2. Our proportion then, because what they gave us is that on the map it is 2 inches, has to be in the numerator, and we can solve for x. So x would be equal to 4 miles in this case. And we'll have more opportunities to solve problems like this. So I'll give you a minute to write down those equations. Okay, let's look at a practice example. The scale on a map reads 1 centimeter to 200 meters. We're going to find the actual distance if the distance measured on the map is 7 centimeters. So again, let's use words to describe what our scale is, what we're comparing. And in this case, we're comparing the map or the drawing to the actual. So the smaller units, centimeters, is on top, and the meters in real life is on bottom. We can see easily the scale right here, and we can put that into the ratio form. So we go ahead and put 1 to 200. In forming the proportion, we need to put the 7 centimeters that they give us in the numerator because it relates to the distance that is measured on the map. So that number has to correlate in the same position on the right-hand side of the equal sign as the centimeters did on the left-hand side ratio. Okay? So then we cross multiply to solve it, and we would find 1x is equal to 200 times 7, or 1,400 meters for our final answer. Let's look at another example. We're going to find the actual distance from LA to Houston. LA is the dot, Houston is the star. We can see the map scale given right here. So 1 inches equal to 300 miles actual. So if we set up the ratio so that we always do the map dimension that we measure in inches to the actual, which is in miles, we could then use a ruler, or I know in geography I think you guys took on a piece of paper and lined it up with the scale that they show right here. You line it up with that, and then how many times will that fit between those two locations? Kind of like this. 1, 2, 3, 4, 5. So what we've measured in that tiny quantity, that tiny segment, is 5 inches. So now the key is setting up the right-hand ratio so that that 5 is in the right location, numerator or denominator. How do we know which one we want it in? Okay, so our 5 inches would be on top in the numerator over x in miles. Using the cross products, we know that 1 times x is equal to 300 times 5. When you multiply, you get 1,500 miles as your solution. Three more examples. Here we go. The scale of the house blueprint below is to be 1 inches equals 8 feet. The actual dimensions are given. Notice the actual dimensions are in feet. The dimensions are 80 feet by 30 feet. Find the map or blueprint dimensions of X and Y. So we're given the scale, 1 inch equals 8 feet. We'll put that in a ratio form. We're going to use the map or the inches to the feet, just like we've been doing. We've been putting the smaller or the model or the map on top and the larger on the bottom. As long as you're labeling it, it's okay, to mix that up if you look at it in a different way. Just as long as what you're putting on both sides of the equal sign is comparing in the same way. So we're always, in this case, because we set it up as inches to feet, both ratios will be inches to feet. So for the length, we use the scale, that 1 to 8. So 1 inch to 8 is the scale. What we were given for the length is the 80 feet. So that's the actual feet right there. And so what's missing is the inches. It's kind of like that little example we talked about relating to the last problem. Since the inches are missing, the map dimension is missing, our final unit will be inches because we already know how many feet it is in real life. So we cross multiply. We get 80 is equal to 8x. When you have this problem like this, we know that we're undoing multiplication, so we're dividing both sides by 8. The actual map length on the blueprint would be 10 inches. For the width, we set up and use the same scale, 1 inch to 8 feet. But in this case, the width is different because we're comparing it to the map or the blueprint of Y to 30 feet in actual width. Cross multiply again, 1 times 30 is equal to 8y. So that when you divide both sides by 8 this time, we'll get a decimal, because 8 does not divide evenly into 30. Just round it to the nearest hundredths place. I'll usually tell you if I'm wanting it to be to the nearest whole number, but in this case it's a terminating decimal, so 3.75 inches is an accepted value. Next example. If you buy 1 can of pineapple chunks for $2, then how many can you buy with $10? So first we have to think about in words what kind of a ratio we want to use. So if you're choosing to do a, let's get rid of that, can to dollar ratio, the first thing that we have is an implied ratio that you can buy 1 can for $2. So our second ratio then will help us answer the question of how many can we buy with $10, and the 10 would go in the denominator and the variable in the numerator. With cross multiplication, we come up with an equation so that when we solve the equation, we know that the number of cans is 5. Again, we use problems like this with really easy numbers so that you can practice putting them into proportion, so you can practice the mathematics behind it. And then you can say to yourself, well, that makes sense, because mentally I could figure that out without having to write all that down. But if we can think about it in a way and practice it in an equation, when all of a sudden we lose the ability to do the mental math, we have a strategy to use that we know will work every time. That's where setting up the proportions becomes a useful skill, right? A way to use our math to solve other problems. So let's give another example a try. Shauna reduced the size of a rectangle to the height of 2 inches. What is the new width if it was originally 24 inches wide and 12 inches tall? So if we do a height to width ratio, we know, based on the information they give us, 12 inches tall relates to the height. Our width is 24. To get the solution, we know that she reduced the size of the height. So this number, 2 inches, relates to the height and has to go in the numerator. So what we're missing then is our width down here on bottom. That's our variable, our x, w, whatever you want it to be. To solve this problem using cross products, we have 12w is equal to 48. Dividing both sides by 12, we get the width of 4 inches. All right, that was the last